So let's continue on with this example. We've done the derivative and set it equal to 0. And hopefully you're noticing that there's a GCF of 6. So I'm going to factor out 6. And I want to know when this equation is 0. So I can divide both sides by 6 to remind myself that that 6 doesn't do anything to help make the function 0. So I don't need to take it into consideration when I'm trying to find out when this is equal to 0. So I'm going to have x minus 4 and x plus 3 equals 0. So I use my zero product property and I say either x minus 4 is 0 or x plus 3 is 0. So that gives me my two critical numbers, x equals 4 and negative 3. So I'm going to make my number line and put negative 3 and 4 with x is the label for this row because these are representing x values. So then I want to add some information about f prime. And so far I know that when x is negative 3, f prime is 0. And when x is 4, f prime is 0. And then let's leave enough space to add some more information and then do our interval testing. So we have negative infinity to negative 3. So I would pick for my test point negative 10. And I want to know if the derivative is positive or negative. So I'm going to test f prime of negative 10. So that's going to be 6 times negative 10 squared minus 6 times negative 10 minus 72. So negative 10 times negative 10 is 100 times 6, 600 plus 60 minus 72. So that's clearly going to be positive. So everywhere on the interval from negative infinity to negative 3, the derivative is positive. Then let's look at our next interval from negative 3 to 4. 0 is an option in that interval, so I'm going to pick 0 because I can easily see that f prime of 0 is negative 72, so that's negative. So everywhere between negative 3 and 4, the derivative is negative. And then let's check our third interval from 4 to infinity. And I'm going to pick my test point of 10 and check the sign of f prime when x is 10. So I'm going to have 100 times 6, 600 minus 60 and minus 72. So that's going to be positive. And my derivative is positive from every x value from 4 to infinity. So now let's indicate what's happening with f, the function. If the derivative is positive, the function is increasing. So wherever the derivative is positive, the function is increasing. And where the derivative is negative, the function is decreasing. Well, at x equals negative 3, we can see that the function's rising and then has a place where the derivative is 0 and then falling. So that's going to be a local max. And then the function is decreasing, then hits a place where the derivative is 0, then rises. So this is going to be a local min. So this is the first derivative test. All this work that we've just done here is the first derivative test. So now let's talk about how we actually answer this question, because we've found the location of each extremum. So when x equals negative 3, f has a local max. And when x equals 4, f has a local min. So that's the answer to the location of each local extremum. Then we are also asked and the value of the function at this extremum. That means not the derivative. I want to know what f of -3 is and what is f of 4. So those are the value of the function at the extreme point. So for f is -3, we're going back to the function here and putting -3 in everywhere you see x. And I'm getting 150. And then when x is 4, I'm getting 2 times 4 cubed minus 3 times 4 squared minus 72 times 4 plus 15. And I'm getting negative 193 for that. So 150 is the local max value of f. And 193 is the local min value of f. So let's put all that together, and another question that can be asked is, where is that maximum point? So the max point has two coordinates. It's going to be -3, 150. And the min point is going to have two coordinates. Is going to be 4, -193. So let's jump over to Desmos real quick. And look at the graph. So here's the graph of that function. And when x is -3, see that we have a max point. And in fact, Desmos will tell you the coordinates of the point, so you can use that to check your work. And then when x is 4, we have a min 4, -193. Okay, so this next example was chosen for several reasons. It's going to illustrate several important points. So the first thing we need to do when we're using the first derivative test is find the first derivative. So this looks like a quotient rule. So I'm going to have u, the top function is x cubed, and x cubed plus 1 is going to be the bottom function. Then I'm going to take the derivative of u, 3x squared, the derivative of v, 3x squared. So now I'm going to write my derivative is f prime of x, and I'm going to put my denominator first because way too often I forget all about it. So now I'm going to cross multiply, and I'm going to have x cubed plus 1 times 3x squared minus x cubed times 3x squared. So we need to simplify this because we're going to want to know when it's 0. So we have 3x to the 5th plus 3x squared minus 3x to the 5th over x cubed plus 1 squared. So these 3x to the 5ths cancel out, and I have 3x squared over x cubed plus 1 squared. So this is my first derivative. So I'm going to write it here because it's so important that critical numbers or critical values are values of x that make f prime equal to 0 or cause f prime to be undefined. And if you forget that on this problem, it would be a disaster. So f prime is going to equal 0 when 3x squared over x cubed plus 1 squared is 0. Well, the denominator never causes a fraction to be 0. So this is going to only happen when x is 0. So that's our first critical value, is when x is 0. Well, this function is undefined if x cubed plus 1 is 0. Well, that can happen if x equals -1. So x equals -1 is also a critical value. So this function has two critical values, -1 and 0. And if you're missing one of these, it's going to be impossible to get the rest of the problem correct. So these are x values, and then we need to write about f prime. Well, when x equals -1, f prime is undefined. It's not 0, it's undefined. And when x is 0, then the derivative is 0. Okay, so then we need to look at the sign of f prime. Well, I want you to come up here and look at f prime with me and think about it for a moment. And if you spend 1 minute thinking, you might be able to save yourself 5 minutes of working. Because notice that the numerator is a squared x, always going to be positive, 0 at the very smallest, times 3. So if it was positive, it would stay positive. Divided by a squared quantity, which is also always positive. So this derivative is always positive. So a minute of thinking about it and analyzing and looking and noticing, I can save myself a lot of work, and now I know the derivative is positive everywhere the derivative is defined. So here's what I know about the function. The function is also undefined at -1 because the denominator of the function would be 0 if x was -1. So the function is increasing, and then this is actually a vertical asymptote since it makes the denominator of the function 0. Then we're increasing. We have a spot where the derivative is 0, but then we're still increasing. So this function doesn't have any maxes or mins, right? So find the location of each local extremum. There, oops, wrong function. Let me go back up to the problem we're working on. There are none. Okay, so let's see what this graph looks like. So here's the graph. It has a vertical asymptote at x equals -1. To the left of that, it's always increasing. And then to the right of the vertical asymptote, always increasing. At x equals 0, we have a momentary flat spot, but then always increasing. So that problem, there are no extreme values. Okay, but there are two critical values. So if you were asked what the critical values were, you'd have to come up with 0 and -1. Okay, then let's look at this third example. And the +1 part of the derivative doesn't do anything to change the derivative. So the derivative is going to be about this product where u is x cubed and v is the e to the 4x. So then the derivative of the u is 3x squared. The derivative of the v is 4e to the 4x. So then my derivative f prime of x is going to be e to the 4x times 3x squared plus x cubed times 4 times e to the 4x. Well, I want to know when that's 0, so we always want to try to factor to turn a sum or a difference into a product. So I'm going to factor out e to the 4x, each of these terms has in common. And then they also both have an x squared. So I'm going to factor out x squared e to the 4x. That's going to leave a 3 in the first term and 4x in the second term. Okay, now we need to do a little bit of analyzing. Think about the zero product property. I have x squared multiplying e to the 4x multiplying 3 plus 4x. So either x squared is 0, e to the 4x is 0, or 3 plus 4x is 0. So let's think about when is x squared equals 0. And that's only going to happen when x is 0. Then let's think about e to the 4x. And this is one of the reasons I wanted you to draw a few graphs of e to the x and get more familiar with that function, because it can be really useful here when you're trying to solve an equation. If you know e to the 4x looks like this, and so y is positive no matter what x is, so it can never equal 0. So e to the 4x is never going to make that product 0, so it doesn't contribute anything to the solution set. And then we have x equals negative 3/4. So we have two critical numbers, negative 3/4 and 0. So these are x values. And when x is negative 3/4, the derivative is 0. And when x is 0, the derivative is 0. So then let's find what the derivative is in each of these three intervals. So from negative infinity to negative 3/4, I would pick my favorite, negative 10. And then I'm going to come back and look at this derivative and go, you know what, this x squared and the e to the 4x part, that part's always positive. Right? We just said e to the 4x is always positive. And earlier we talked about x squared is always positive, so their product is always going to be positive. So the only thing I need to check is 3 plus 4x. Is 3 plus 4x positive or negative? Because that's going to decide the sign of the whole derivative. So let's put negative 10 in for x. And that's clearly going to make it negative. So everywhere in the interval from negative infinity to negative 3/4, the derivative is negative. Then from negative 3/4 to 0, let's pick negative 1/2. 3 plus 4 times negative 1/2, that's going to be positive. So everywhere from negative 3/4 to 0 on the x-axis, the derivative is going to be positive. And then I have from 0 to infinity, so I'm going to pick 10. 3 plus 4 times 10, clearly positive. So notice there's not a predictable pattern. Here we have negative, positive, positive for the derivative. So let's see what we know about the function. We know that the function is decreasing when the derivative is negative. It's increasing when the derivative is positive, and increasing when the derivative is positive. So at x equals negative 3/4, we have a local min. That's our only extreme value. Because at x equals 0, it does some kind of little bump and then goes up again. So it's not a critical value. I mean, not an extremum, sorry. So the location of each local extremum. At x equals negative 3/4, f has a local min. And the value of the function at this would be f of negative 3/4. So you would have negative 3/4 cubed e to the 4 times negative 3/4 plus 1. So that's going to be negative 27/64 e to the negative 3 plus 1. And that's the exact value. You could get a decimal approximation, but I'm not going to ask you for that. Okay, so I'm going to pause the movie here and do one more movie for the application problems.